This is Lenicia, and you are about to view my dad, Mr. Witt, in Fort Bend Tutoring, where personalized math tutoring is the solution.
Hello, ladies and gentlemen. This is Mr. Witt with Fort Bend Tutoring, and today's lesson is going to be about simplifying square roots. So let's check it out, shall we? Okay, ladies and gentlemen, the first thing we want to do is describe the radicals. What are we looking at? So anytime I'm looking for a square root, here I have different parts of the problem. One, I have the radical symbol, all right? So that's this symbol right here, okay? Big check mark, a little extension there. That's a radical sign, ladies and gentlemen. So the different parts of your radical is going to be the index. That's going to be the root that you're looking for. You also have the radicand, that value underneath the radical symbol. And then, of course, you have the radical sign itself. All right. There's another way that this problem can be given to you, however, and it is the following. Notice that we still have the square root sign, the radical, and we have our same radicand of 36, but notice how the index is not being shown. Anytime you do not see an index, you can assume that the index is 2, meaning that you're looking for a square root. You're looking for a root of 2. So that's what you should be aware of. And lo and behold, ladies and gentlemen, the number that when multiplied against itself, that'll give you 36 is 6. That's right. 6 to the second power, meaning 6 times 6, is 36. So when I'm trying to find the square root of 36, remember, I'm looking for that number, that root, that when multiplied against itself will give me 36, and in this case, it'll be 6. Okay, ladies and gentlemen, let's continue. I bet you're wondering, Mr. Witt, and I'll be like, yeah. How do you know what the perfect squares are? How do you know what number to look for? How do you know what number to use in order to simplify your problems when you're dealing with radicals? And my answer to you is you have to memorize them. And you know what, ladies and gentlemen? That's the biggest thing that's not being told to students worldwide. In order for you to be successful in simplifying radicals, period, especially square roots, you must have your perfect squares memorized. That's right. Now, I'm going to take it easy on you, and I'm only going to give you the first, let me show you. I'm giving you the first 18 perfect squares in this, all right? So that's what I have for you. There you go, there you go, there you go. These are the first 18 perfect squares. However, I would strongly suggest that you as a math student learn your perfect squares, memorize them all the way up to 25. All the way up to 25. Now, let me give you the reality of that situation. If you know your perfect squares up to 15 squared, notice I have 15 squared equals to 225. So if you know your perfect squares from 1 squared all the way to 15 squared, you'll probably be an A student. Yeah. A student, high B, depending on the level of class that you're in. But if you want to kill your class, you want to kill these problems, you want to master them, yeah, you'll learn your perfect squares all the way up to 25. Just saying. 25 times 25 equaling to 625. You want to know them because if you know them, you'll be better at all of mathematics because there are a lot of math concepts that involve you knowing your perfect squares. Just saying. All right. So if you want to know the secret to simplifying square roots and or radicals, learn, memorize your perfect squares. That's right. Okay. Let's dig into some problems, ladies and gentlemen. First off, 1a, we have the square root of 16. Now these, ladies and gentlemen, you just want to know them right off the bat. Hey, square root of 16 is a perfect square, therefore the answer is 4. That's it. All right? And that's what I mean by recognition. Unless you can recognize a perfect square, you're going to have a harder time simplifying these problems. So memorize that the perfect square, 16, has a square root of 4. That's right. It took 4 times itself to give you 16. Then 1b, we have the square root of 49. The square root of 49 is 7. Knew it on sight. That's what I'm saying. Memorize them. Then you have 1c, the square root of 15. Now 15 is not a perfect square. So as far as simplifying them cleanly, this is already simplified. So the answer will just be the square root of 15. Now there are some classes that'll have you simplify this into decimal notation. They'll have you round it to the nearest tenth. And I'll give you a video on how to do just that. Matter of fact, I'll put a link right beneath here. All right. Simplifying square roots to the nearest tenth. Well, other than having to simplify to the nearest tenth, your answer of the square root of 15 will be just fine because there are no longer any factors of 15 that are perfect squares, so it can't be simplified any further. So as far as this lesson is concerned, our answer for 1a is 4, our answer for 1b is 7, and our answer for 1c is the square root of 15. In other words, it can't be simplified any further. All right, let's continue on. Here we have our next problems. All right, in problem 2a, we have the square root of 16/25. There are a couple of strategies in order to simplify a square root when you're dealing with a fraction as your radicand. And that is, you can either simplify the fraction first, or you can actually split the radical itself between the numerator and the denominator. And that's exactly what I'm going to do in this problem here. I'm going to break this up into the square root of 16 over the square root of 25. Once I've done that, I can take the square root of 16, which is 4, and the square root of 25 is 5, so that my answer here is 4/5. And that's it. All right. So what I did was, because I could not simplify 16 and 25, in other words, they didn't have anything in common, I was able to split this radical between the numerator and the denominator, and that gave me 4/5 after I took the square root of 16, which is 4, and I took the square root of 25, which is 5. And that's it. So that's 4/5 for 2a. Let's look at the next problem, 2b. For 2b, we have the square root of 75/20. Now, looking at your fraction 75/20, I know that both of these numbers can be reduced by 5. And that's exactly what I'll do. So I'll rewrite this radicand as 15/4 after reducing the 75 and the 20 by 5. 75 divided by 5 is 15. 20 divided by 5 is 4. Now, since the 15 and 4 no longer have anything in common, what I'll do next is I'll split the radical sign. I'm going to split it between the numerator and the denominator. I'm going to expand it, and I'll rewrite this as the square root of 15 divided by the square root of 4. Then, knowing that the square root of 15 can't be simplified any further, it's not a perfect square, and it doesn't have any factors that are perfect squares other than 1, I can then simplify the denominator. The square root of 4, which is a perfect square, by the way, is 2. So my answer here is the square root of 15 divided by 2. And that's it. All right, that's the answer. Done and done. I will tell you this, ladies and gentlemen, that you could write this another way. You could write it as 1/2 the square root of 15. But the first method was just fine as well. So unless you want to try to be fancy here, you can write it either way. Square root of 15 divided by 2, or you can say 1/2 square root of 15. Either way is cool. All right, so that does it for 2b. Let's keep it moving. All right, let's keep things moving here. Next problem. Problem 3a, we have the square root of 8. All right, and we want to simplify that. Now, according to the chart that I gave you at the beginning of the tutorial here, 8 is not a perfect square. However, there is a factor of 8 that is a perfect square. Do you know what that is? Very good, ladies and gentlemen. It's 4. Exactly, it's 4. So I'm going to expand the square root of 8 into the square root of 4 times 2. Because 4 is the largest perfect square that'll go evenly into 8. Remember, our index is 2 here for a square root, so I'm looking for a perfect square within the number 8 there. All right, so I'll be taking the square root of 4, which is 2, all right, and what's left over is going to be that radicand of 2 underneath there. So I'm done. That's it. It'll be 2 times the square root of 2. Done and done, ladies and gentlemen. And that's how you simplify the square root of 8. Just like that. Let's look at our next example. 3b. I have the square root of 54, and the largest perfect square that'll go evenly into 54, ladies and gentlemen, is 9. That's right, it's 9. So what we're looking for is we're looking for the largest perfect square within 54. We're looking at all the factors of 54 and looking for the largest factor that happens to be a perfect square. And in this case, it will be 9. So I can expand 54 into the square root of 9 times 6. From there, the square root of 9 is 3. So I'm left with 3 times the square root of 6. That's the answer there. Then, let's keep it moving. 3c, ladies and gentlemen. I have the square root of 75. 75 is not a perfect square. It's not on that list that I gave you at the beginning of the tutorial. So, being as though it's not a perfect square, my next step is to see if I have any factors within 75 that are perfect squares. And lo and behold, we do have one. And that's 25. 25 is the largest perfect square that will go evenly into 75. So I'm going to expand this into the square root of 25 times 3. And next, I'll be taking the square root of 25, which is 5, by the way, and that leaves me with the radical 3. And that's it. Done and done, ladies and gentlemen. Let's go ahead and put some boxes around these answers here. I like boxes around my answers. Just saying. So 3a, we start out with the square root of 8. That simplifies to 2 times the square root of 2. We then, in 3b, had the square root of 54, which simplifies into 3 times the square root of 6. And for 3c, we had the square root of 75, which simplifies into 5 times the square root of 3. Done and done. All right. Let's keep it moving. Let's keep this thing moving here. In our next example, we have 4a. We have 2 times the square root of 9. Now notice, this is the first time I'm showing you an example that has a coefficient in front. The number in front of the radical is simply multiplying, okay? So it's multiplying on the result of the square root of 9, whatever that may be. So anytime anything comes outside of this radical sign, it has to multiply with that coefficient of 2, the number in front of the radical sign. So let's check it out. Let's see what happens here. So for starters, I'll have 2 times the square root of 9, ladies and gentlemen, is what? Very good. Very good. It's 3. Good job. Good job. Way to scream into the TV or iPhone or mobile device, Android, or whatever, iPad, whatever you're using. There you go. Way to scream into that thing there, because I heard you. So 2 times 3 gives me 6. There you go. That's the answer. All right. So recapping on this problem, we had 2 times the square root of 9. We took the square root of 9, which is 3, and then we multiplied 2 times 3 to get 6. And that's it. Done. Yeah, we're going to keep it moving. 4b. 4b. In 4b, we have the following. We have 5 times the square root of 64. 5 times the square root of 64. I know that 64 is a perfect square. This number is on that list from the beginning of the tutorial. Oh, yes. It is 8. Yeah, the square root of 64 is 8. So I'm going to rewrite this as 5 times 8, being the square root of 64. From there, we'll multiply. So I have 5 times 8, which gives me a result of 40. And that's my answer, ladies and gentlemen. Done and done. That was 4b. All right, let's keep things moving. Hopefully you're enjoying this, all right, because I know I am, right? So here we have 5a. In 5a, we have 3 times the square root of 50. Now, 50 is not a perfect square. However, in simplifying 50 and looking at all the factors of 50, I do find that the largest perfect square within 50 is 25. So I'm going to expand this. I'm going to rewrite it as 3 times the square root of 25 times 2. Oh yeah. Then taking the square root of 25, this 3 will then multiply times 5, because the square root of 25 is 5, and what's left underneath the radical sign is the number 2. Okay? From there, you'll multiply this out, and 3 times 5 will give you 15. And what's underneath the radical is still 2. So my answer here is 15 times the square root of 2. Done and done. Problem 5a. Next, we have 5b. And in 5b, I have 11 times the square root of 24. The largest perfect square within 24, ladies and gentlemen, because 24 is not a perfect square, is 4. That's right. 4 is the largest perfect square that'll go evenly into 24. So I'm going to expand this. I'm going to rewrite it as 11 times the square root of 4 times 6. Just like that. From here, taking the square root of 4, I'll end up with 11. I hate that 11. I'm going to fix it. I'm going to fix that 11. There we go. 11 times 2, being the square root of 4, times that square root of 6. Then multiplying the 11 times 2, we'll end up with 22 times the square root of 6, and that's my answer. That's it. That's it. There you go. So once again, recapping 5b, I had 11 times the square root of 24. We looked for the largest perfect square that goes evenly into 24, and that's going to be 4. So I expanded that 24 into 4 times 6. Then I took the square root of 4, which is 2. That multiplies with the 11, that coefficient outside of that radical sign. And 11 times 2 gives me 22 times the square root of 6, and done. That's the answer. You got it. All right. So let's see what else we have for you. Next, we have some radicals. We have some square roots that involve variables. So let's check out how to solve these problems, okay? Now, anytime you're simplifying radicals, especially square roots, please keep in mind that your index is 2. That's right. I'm looking for all of my exponents to be a multiple of 2 in order to simplify it. And in this particular problem, my exponents are multiples of 2 because 2 times 3 gives me 6 and 2 times 2 gives me 4. If you have an even exponent underneath the radical sign and you're dealing with a square root, you can take the square root of it. In other words, a to the 6 is a perfect square, as well as b to the 4th power is also a perfect square because its exponent is even. So, in order to simplify this, you simply divide the exponents. That's it. You'll say that 6 divided by 2 is 3, so this leaves me with a to the third power. Then 4 divided by 2 is going to give me 2, so that'll be b to the second power. In other words, to take the square root of a variable and its exponent, you simply take half of it. That's it. Take half of the original exponent. So 6 divided by 2 is 3, 4 divided by 2 is 2, and I'm done. I'm done. That's the answer. That's it. A to the third power, b to the second power. Done and done. All right. Now, of course, that was an easier problem because, of course, they gave you perfect squares to begin with. All right. But what happens when your exponents are not all perfect squares? Let's see. Remember, my index, especially if they don't show me on the original problem, they just have the radical sign there. I can assume that the index is 2, meaning that I'm looking for a perfect square. Well, as it turns out, because I want these exponents to be even in order to take the square root of it, I'm looking for the largest multiple of 2 that'll go into 7 without going over, all right? And I'll be using that to my advantage to expand the problem. So the largest multiple of 2 that'll go into 7 without going over is 6. That's right, 6. So I can expand this into x to the 6th power times x to the first power because it's that 6 plus 1 that it gives me back my original 7. So I'm expanding this to show the largest multiple of my index, which in this case is 2. So I break it down into 6 and 1. That gives me my original 7. I'm bringing down this y to the 10th power because it's already an even exponent. I know I can divide this 10 by 2 evenly. So it's fine the way it is. However, with this z to the 15th power, the largest multiple of 2 that'll go into 15 without going over will be 14. So I'll have this rewritten as z to the 14th power times z, just like that. Now, every variable that has an even exponent, those are going to be your perfect squares that you can find the square root of. So x to the 6th power, z to the 10th power, z to the 14th power. Yeah, I'm about to take the square root of those. Yeah, because they have even exponents. So let's see what that looks like. The square root of x to the 6th power is going to be x cubed. I know that because all you have to do is take half of that even exponent. The square root of y to the 10th power is going to be y to the 5th power. Then, taking the square root of z to the 14th power, I end up with z to the 7th power. Once you've taken the square root of x to the 6th power to get x cubed, y to the 10th power to get y to the 5th power, and z to the 14th power to get z to the 7th power, the remaining variables underneath the radical remain there as your radicand. So you'll end up with x, z underneath the radical sign. So your answer is x cubed, y to the 5th power, z to the 7th power times the square root of xz, and done. That's your answer. All right. In our next example, we have 7a. In example A, we have 5 times the square root of 27a to the 3rd power, b to the 6th power, c to the 14th power. Once again, our index is 2. We're looking for perfect squares, so we want to expand what's underneath the radical sign, our radicand, so that we can highlight our perfect squares underneath the radical sign. So I'll be rewriting this as 5 times the square root of the largest perfect square within 27 is 9. So I'm rewriting this as 9 times 3. The largest perfect square within a to the 3rd power would be a squared. That leaves me just one a left. B is already a perfect square with b to the 6th power, and our c is to the 14th power, and it's also a perfect square, so it doesn't need to be changed any. Remember, anytime your exponent is even, you already have a perfect square. Since a to the 3rd power was an odd number, I was looking for the largest even number within 3, and that's going to be 2. All right, and that left me with 1 over. From there, I'll be taking the square root of the 9, a squared, b to the 6th power, and c to the 14th power, and bringing those results down to multiply with my 5. So I have 5 times the square root of 9 is 3. The square root of a squared is a. The square root of b to the 6th power is b cubed. The square root of c to the 14th power is c to the 7th power. And that's going to leave me with the square root of 3a. All right. From there, I'll be multiplying this out together, the coefficients in front. 5 times 3 is going to give me a result of 15a, b to the 3rd power, c to the 7th power, times the square root of 3a, and then that's my answer. All right, let's go ahead and move it over so you can see what I'm talking about here. We had 15ab cubed c to the 7th power times the square root of 3a, and that was the result of us multiplying that 5 times 3, and then of course just bringing everything else over. I'm going to put a red box around this. All right, so that's my answer there. Done and done. Good stuff. Next we have 7b. In 7b, I'm once again trying to simplify the square root. So I'm looking for perfect squares. I notice that 4 is a perfect square underneath the radical sign. I also notice that I have an odd exponent on my variable e, and that f has an even exponent of 16. So that's already a perfect square. So I'll be rewriting this as 12 times the square root of 4d e to the 10th power, the largest multiple of 2 that goes within 11 without going over. That leaves me with 1e. And I also have my f to the 16th power. Then, taking the square root of the 4, e to the 10th power, and f to the 16th power, I'll end up with 12 times the square root of 4, which is 2, times the square root of e to the 10th power, which is e to the 5th power, times the square root of f to the 16th power, which is going to be f to the 8th power. That's going to leave me with a square root of d e. And that's it. Okay? Those are the only things that were left over. After that, I'm going to go ahead and multiply 12 times 2 to give me 24, and bringing down the rest of the problem, I'll have e to the 5th power, f to the 8th power, times the square root of de, and this is my answer here. Done and done, ladies and gentlemen. That's it. That was problem 7b. Let's recap over this. In 7b, we had 12 times the square root of 4d e to the 11th power, f to the 16th power. I knew that 4 is a perfect square. That's on my list from the beginning of the tutorial. However, my exponents on my variables were odd for the most part. I had d to the 1st power. I also had e to the 11th power, and I also have f to the 16th power. That being the case, I broke up this e to the 11th power into e to the 10th power times e. Multiplying those back together, you'll get that e to the 11th power, because this e is to the 1st power, and you add your exponents when you're multiplying. So I know that that's the equivalent expression, e to the 10th power times e. The f to the 16th power I left the same because it already had an even exponent, so I can take the square root of that. From there, we took the square root of 4, which is 2, so it came on the outside of the radical. The square root of e to the 10th power, 10 divided by 2 is 5, so I end up with e to the 5th power. Taking half of 16, I end up with f to the 8th power, and what was left over was this d as well as this e inside of the radical. So that's the answer. After I multiply 12 times 2, I end up with 24, e to the 5th power, f to the 8th power times the square root of de, and done. That does it for that problem. So, ladies and gentlemen, that does it for simplifying square roots. We gave you a lot of examples, so please, please, please give us a lot of positive feedback. We would really appreciate that. So please rate, comment, and subscribe. If you're able to, please donate. It helps us bring you more free math tutorials on our YouTube channel, Fort Bend Tutoring. Peace.
Thanks for watching. Please rate, comment, and subscribe. Visit our website at www.tutormemath.net.